Oh, you can sit here.
All right, well, thanks for the invitation. It's a real pleasure to be visiting Penn. I haven't given a talk here, so I might not be invited back. This visit was fun. So, but I'm going to start with an introduction to algebraic K-theory because I think it's useful, especially because the modern point of view on algebraic K-theory takes as an input a lot of higher category theory, which I won't get into in detail, but I just want to give you some idea of what the technology is that we input nowadays to study algebraic K-theory. So the first question I'm going to address is, what is algebraic K-theory? And why would we care about it as mathematicians? So maybe the answer is that it's a powerful and quite general cohomological, put co in parentheses because it really depends. If you're thinking geometrically or algebraically, cohomological invariant of, and now here we get to the geometric versus algebraic distinction, rings, or so algebraically rings, or say abelian categories, the type of things that come up when you study rings, like categories of modules over a ring, or varieties, schemes. These schemes might even be derived or whatever. You can really plug just about anything into algebraic K-theory because really what it takes as input is some type of category. It's a category that you associate to one of these algebraic or geometric objects. That's what I meant by general. What did I mean by powerful? Well, powerful means that it retains lots of information. But that comes as a trade-off. Namely, it's quite hard to compute. So I'll tell you something about what computations we actually do know in algebraic K-theory. Really, the only ones that we know haven't changed that much since the days of Quillen, who started off computing the algebraic K-theory of finite fields, and that and slight variants thereof are really the only full calculations of algebraic K-theory that we have. Anyway, if we have some, let me call X my algebraic or geometric object, you associate to X some sort of category of, say, perfect complexes. Of vector bundles. Or if X were a ring, maybe I would say projective modules. And maybe I'll just call that category C because really K-theory doesn't care what type of category you input into it. So it's set up as a functor from some types of categories. All that's really crucial here is that the categories have a notion of exact sequence in it. Waldhausen formalized this by inventing something that is not surprisingly called a Waldhausen category. And it goes to, well, the category of spectra. But if you don't know what a spectra are in the sense of homotopy theory, you can think of this as spaces with possibly some negative homotopy groups as well. There's a notion of, well, there's a notion of a de-looping of a space, which allows you to talk about spaces that have negative homotopy groups. The key role of spectra is that they represent cohomology theories on spaces. There's no need to go through the construction. There's a lot of ways that you can construct K-theory. It's not particularly sensitive to which one you choose, but let's just say that then given an input category C, which typically comes from algebra or geometry, then its K groups, Kn of C, are the homotopy groups of this space or spectrum that I associate to my category C. And let me give you now some history of how K-theory developed along with some calculational results. So the history is, first of all, it was invented, well, K0. So just the pi zero of this K-theory space. Well, this was invented by Gepner to solve the Riemann-Roch problem. In geometry, which is something about comparing the push forward in K-theory versus the push forward in the Chow groups of algebraic cycles on a variety. They don't quite push forward in the same way. The difference is measured by the Todd class, and the conceptual proof that Gepner envisioned used the very first algebraic K group, which if I plug in a ring R, it's K0 of R is the Grothendieck, it's the group completion. I'm adding inverses to, let's just say, the monoid of isoclasses of projective R modules. And if R were a scheme or something, not an affine, there would be some similar thing I could say involving vector bundles on R. But I'm adding inverses. In this case, because I have projective R modules, my category is the category of projective R modules in this case. There aren't any non-split exact sequences. But in general, K0 of C does two things. It splits all the exact sequences in C and group completes the monoid of isoclasses of objects. So K0 is pretty easy invariant to compute, at least compared to the other K groups, which don't have such a nice description. I mean, I didn't write it out in the formula, but I'm telling you in words what it does. So, the higher algebraic K-groups were first correctly defined. There were a number of attempts at this by Quillen in I guess 1973 or 74, let's just say the 70s, in his paper, Higher Algebraic K-Theory. And there's also lower, as in negative, algebraic K-groups that were defined by Bass. And now they fit together, I mean, around the same time Bass defined the negative K-groups. Let me just say before I mention that these definitions turn out not to be ad hoc, let me just mention Quillen's motivation for defining the higher algebraic K-groups. Quillen...
Don't forget the yellow microfiber.
Oh, right.
Next time.
Well, we can still... That's way better. So, even before Quillen managed this definition, he computed the following theorem from 72. That if you put, well, Kn of Fq, if, let's say Q is P to the K, the finite field in order of P to the K, that this is, well, it's Z, if n is 0, you can compute that from what I already told you. It's 0 if n is less than 0. There are no negative K groups in this case, and the reason for that is because this is a regular ring. It doesn't have any singularities, and negative K groups detect singularities in your ring or your scheme. And, well, it's also 0 if n is even, and it's Z mod Q to the n minus 1 if, maybe I should say n, if n is equal to 2n minus 1. So that Quillen had this calculation based on the group cohomology of GLNFQ and representation theory, which then he wanted to put into context, so he succeeded in successfully defining the higher K groups. Now, you don't always expect the negative K groups to vanish. For example, if I take the nodal cubic curve like that, let me just call this X, it has a singularity right here, obviously, and its K minus 1, as defined by Bass, is equal to the integers. You can find examples of things that have infinitely many negative K groups, although a conjecture of Chuck Weibel, which has recently been proved in its full generality, says that if you have a smooth scheme of Kroll dimension D, then the negative K groups will, sorry, I should have said the scheme of Kroll dimension D, then its negative K groups will be 0 after minus the dimension.
Who proved that?
Well, it was a sequence of many people. Like Christian Hasemeyer was the first paper, then Szynski, then Strunk and Tama. I mean, it was incremental, but now it's fully proved. Let me discuss that after the talk. Just because the list is too long. Let me give you another example, not of negative K-groups, but of a calculation that we'd like to know. The K-theory of Z is fully computed except in degrees n equals 4m, so degrees multiple of 4, where conjecturally k 4n, maybe we should put 4n, of z is 0 for n greater than 0. And this looks like a fairly innocuous statement, but this is equivalent to the Kummer-Van Diver conjecture. In algebraic number theory, which is a conjecture about the class number of the maximal real piece cyclotomic extension of the number. So somehow K-theory sees both geometric and arithmetic information. Then Waldhausen came along and showed that you can redefine K-theory more conceptually for any so-called Waldhausen category. Incidentally, he was doing this in order to obtain information about manifolds. And an example of the type of thing that you can put into the K-theory machine of Waldhausen is if I have M as a manifold and I take its loop space, I can take the group ring on this group, which is the loop space of my manifold. What is S here? S here is the sphere spectrum. It's the homotopy theorist refinement of the integers. Its pi 0 is the integers, but the rest of its homotopy groups are quite deep and tell you information that should be encoded in the integers had you, instead of group completed the natural numbers, which are what you get when you think about finite sets and only identity bijections. If you group complete rather the category of finite sets and all bijections, you get the sphere. So it's a more structured version of the integers. I could have put Z here as well, because that's a ring, but the sphere is a ring. So I can put in this homotopical version of the ring. I mean, loop sum isn't really even a group. It's only a group in the homotopical sense. Into the K-theory machine. And one of the main theorems conjectured by Waldhausen and proved by Waldhausen amongst others later is that this splits up as the so-called stable homotopy of M. Plus this piece called the Whitehead space of M. And this space classifies stable diffeomorphisms of M, which was a manifold. So somehow K-theory is also telling you geometric topological information. So that's why it's a rich object that occurs in lots of areas of mathematics: algebra, topology, geometry, etc. And it's a strong invariant for all of, it's a strong in general invariant for all of these things. But we still don't have that many computations of K-theory because they just tend to be too difficult to compute.
Could you just say a word about stable diffeomorphisms? So two diffeomorphisms of M are stably equivalent if?
Right, if I cross them with an interval of some high power. It means I take the union over M cross I to the N, and then I look at diffeomorphisms relative to some boundary. And that's what that space is. Okay, so how to compute K-theory? So the first is if I have my geometric object written as a union of two opens. And let's say with intersection U, this is the typical place where you would expect some sort of Meyer-Vietoris sequence, and you do get a Meyer-Vietoris sequence like this. So you can, if you knew the K-theory of any three of these, you would be able to get the K-theory of the fourth one. So that's a local to global principle that K-theory satisfies. The other method that we have of computing K-theory, so you can, I stated this in a geometric fashion, but there are also categorical analogs of how you can decompose a category in order to compute it. The other method that we have is by going to the topological cyclic homology, which is in some sense a good linear approximation. And this is called the cyclotomic trace method. And that's really, aside from the K-theory of finite fields, which you can just sort of compute to get yourself off the ground, most of the other computations that we know of either run by trace methods or they run by using some étale or motivic cohomology spectral sequences that converge in the algebraic.
What's the OC?
Sorry?
Which method is the OC?
That's computed via the étale cohomology. Well, you use étale cohomology, you do it with finite coefficients, which lets you compare it to the motivic cohomology. Then there's a spectral sequence from the motivic cohomology to the algebraic K-theory that gives you the answer with finite coefficients. You're good at all finite coefficients except at the prime 2, and at the prime 2 you have extension problems that we're unable to resolve, which is why we have this ambiguity in the K-theory of C. That answers your question. Okay, so now what did I really want to talk about in this talk today? It's, so I'm not going to talk much about trace methods, even though that will come up in a couple things that I state later as the method of proof. I want to talk about a categorical analog of this, which is called localization and devisage, which originally appeared in Quillen's, I guess, 74 paper or 73 higher algebraic K-theory. And also the generalizations of that we use nowadays. So let me just give you a quick heuristic definition. So don't take this literally, but an infinity category C is a category, let me just say, weakly enriched in spaces. In other words, you have to remember that between any two objects of C, you have an entire space of maps and not just a set of maps. And
What does that sentence mean? What's it in a space of, you mean a set of maps with some kind of further structure? That's what you meant by space of maps?
it's, strictly speaking, slightly more complicated than that, but that's a perfectly good way to think about it. And you can actually, I could rigidify an infinity category to actually be a category enriched strictly in topological spaces, where what you said would be actually true on the nose, but that would lead to further problems. So let me just not get into what the exact form is here. But what we really want is the notion of a stable infinity category. Is an infinity category with finite limits and colimits, whatever that means, a zero object, and the defining property of stability is that if I have a square like this, let's say A, B, C, and D, this square is a push-out in C if and only if it's a pullback in C. That's the notion of stability that's relevant here. Examples of this are, so the main example I want to focus on so derived categories of a ring R, or more generally of an abelian category A, are examples of stable infinity categories. Because, well, you can just compute with the, so from this point of view, I should be writing homotopy pushout or homotopy pullback, really. But you can compute mapping cones and that sort of thing by hand in derived categories, and you can convince yourself that a derived category has this property. Another way of saying all of this is that one of the pleasant features of stable infinity categories, these are just conditions on an actual infinity category, but one of the pleasant features is that the suspension of an object, if I have an object A, I told you that C is stable, it has a zero object. If I look at this diagram and I form the pushout, what I get is the suspension of A, which if you're an algebraist, maybe you write like that. That occurs as a natural operation. It's actually this colimit. So if on the other hand I had an object B, and I did the reverse operation of taking the pullback, I would get loops on B, or what, if you were an algebraist, you might write B minus 1. And another way of phrasing stability is that these functors sigma and omega exist, and C is stable if and only if sigma is inverse to omega. In these derived categories, suspension is moving something up by 1, looping is moving something down by 1, so they're evidently inverse operations in this type of set. Anyhow, in modern language, we really want to consider K-theory as a functor from stable infinity categories to spectra. And its defining feature is that, so first of all, just a little fact about stable infinity categories, that if C is a stable infinity category, then its homotopy category of C, I'll tell you what that is. this is the category with the same objects, but Pom in the homotopy category of C from A to B is pi 0. Remember, I told you an infinity category has a mapping space between any two objects. It's just I take the components of that mapping space to get the homotopy category. What's the fact, though? If C is a stable infinity category...
So in old speak, you're looking at homotopy classes of maps of A and B.
Correct. That's exactly right. Correct. But then this is a triangulated, is canonically triangulated. Where the shift functor is this functor. So this remedies the usual defect of triangulated categories that people had been worried about ever since the time of Verdier, when they were invented, which is that the cone operation in a triangulated category is not an example of a colimit construction. It doesn't have a universal property. It only has a weak universal property. The theory of stable infinity categories corrects that defect in two ways. The shift does have a universal property. It's the push out of the two maps to 0. And second, stability is properties of an infinity category as opposed to extra structure on an infinity category, which was one of the other defects of a triangulated category. The triangulation is not properties of a category, it's extra structure on a category. Finally, the other fact that you need to know, this was proved by Schlichten, is that K-theory is not an invariant of triangulated categories. You need, well, let me say, Towen and Vitsozi then showed that in fact it is an invariant of the infinity category. So,
What does it mean to be an invariant of a category?
it means that there's no functor from the category of triangulated categories to spectra or spaces or anything that reconstructs the K-theory that you want. So it was hoped for a long time that it was actually an invariant of the triangulated category. There was an ambitious program to prove that, but that program failed. Okay, so I've tried to motivate why you would care about stable infinity categories in this situation without actually giving you any definitions. But the key point is that there's a notion of exact sequence, or let me call it exact triangle, of stable infinity category. A to B to C, like that. And let me explain that notion really quick, because this is the key ingredient in everything that's going in, well, in proving this type of statement that K-theory satisfies Meyer-Vietoris, or in doing various K-theory computations. So what does it mean to have an exact sequence of stable infinity categories? It means that this first map is fully faithful. So the mapping spaces in this infinity category are equivalent to the mapping spaces of the things in the image of this category. And the map, this exhibit C is the quotient of B by A. And this quotient is, so on homotopy categories, the Verdier quotient of triangulated categories. In fact, you can even detect if I have an exact triangle of stable infinity categories by asking whether or not the induced sequence of triangulated categories is a Verdier quotient. Although that requires an argument, but it's not a hard argument. So I'm just pointing out that it's related to a quite old and quite commonly used construction in triangulated categories, namely the Verdier quotient. And the theorem, which, I don't know, I guess I should attribute to Thomason, although he didn't quite state it in this generality, is that K-theory, as a functor from stable infinity categories to spectra, sends exact triangles, let's just say preserves exact triangles. So in other words, if I had one of these, if I had a fully faithful embedding, and C is the Verdier quotient here, then I'll get an exact triangle of spectra, K of A to K of B of K of to K of C, and that then gives me a long exact sequence in Kgroups. And this sequence a priori continues infinitely in both directions, because there are, like I said, there are examples where there are infinitely many negative K-groups. Those come from very singular objects in geometry. And sort of generically, there are infinitely many higher K-groups, like the example of the finite field. Okay, so Quillen didn't discuss this notion using the language of stable infinity categories. Quillen did this, has the same result for abelian categories. And the whole reason that Thomason needed to refine Quillen's theorem is that for general schemes X, you can't get its K-theory by taking any abelian category. You have to take its derived category of perfect complexes in order to actually compute its K-theory. So Quillen didn't quite have the appropriate level of generality when he was discussing K-theory originally, but he still set out structurally what to expect. So he has the same result for abelian categories. And let me state it precisely. Namely, if A to B this is going to be fully faithful embedding of abelian categories with quotient C, provided that exists in the category of abelian categories. And you need another condition. A inside of B, I'm just going to identify A with its image inside of B for convenience here, is a Serre subcategory. So that means it's closed under extensions, sub, and quotient objects. Then you get an exact triangle of K-theory spectra. Actually, Quillen didn't quite prove that. There can be negative K-groups here. So what he proved it for the the part of the K-theory spectra that are concentrated in degrees greater than or equal to 0, which I'm going to denote by tau greater than or equal to 0. I'm truncating, I'm throwing away the negative homotopical information. Now, you can ask what is the relationship between this general localization theorem of Thomason and this localization theorem of Quillen. And there's an easy answer to that. That goes through the notion of a T-structure. So I'll define T-structures later, at least time permitting, so I'm not even using correct eraser. But let me tell you why you would care first about a T-structure and why it directly relates this Thomason result to this Quillen result. So let me state a theorem. This is a theorem of Barwick, but it was after a conjecture of Niemann, which states that, and is called the theorem of the heart. And it states the following: if I don't know, I guess I call it A. If A is a stable infinity category with a bounded T structure. I didn't tell you what that meant yet. Then you have an inclusion from what's called the heart of the T structure into A. This is an abelian category. This was a stable infinity category. But nevertheless, this induces an equivalence from the K-theory of this abelian category to the K-theory of A. Now, this isn't quite true as stated. I also have to pass to the non-negative pieces of this K-theory spectrum to get that exact statement. So, in particular, if I had A to B to C is an exact triangle of stable infinity categories. And they all have bounded T structures. And the functors respect the T structures, then you would get a big diagram like this, where the rows I really have to restrict to the non-negative parts here, where these are exact.
Go from the middle.
Sorry?
No, I said lift the board from the middle, but you said manage.
Right. And you'd have this one here. So you see that this result is telling you that you can recover one localization type theorem from the other because these will all be equivalences.
Did I miss your explanation of T structure?
You did not. I didn't say.
And did I miss your explanation of the superscript heart?
I didn't say what the heart of the T structure is yet.
Okay, great.
I don't know if that's a positive thing or a negative thing. In any case, I will get to that, but I wanted to mention the first motivator just a little bit. So now we have Schlichting's conjecture. Still unproved. I'm going to call this conjecture A, because it will be one of several that will be relevant to this talk. So Schlichting's conjecture is if A is an abelian category, then K minus n of A is 0 for all n greater than 0. So in the special case of an abelian category, Schlichting conjectures that all of the negative K-theory vanishes, which on the top row, these are all K-theories of abelian categories. Now, I had to only restrict to the non-negative homotopy groups here, so this isn't directly related to the top row. But it would at least mean I could erase these truncations from the top row if Schlichting's conjecture were true. And what is the evidence? Well, K minus 1 of A is 0 for any abelian category, and K minus n of A is 0 if A is Noetherian as an abelian category. For example, modules over a Noetherian ring. Okay, so inspired by Schlichting's conjecture, we introduce, I wanted to say one more thing before I mention that. Just a little warning. There are a lot, I can look at the bounded derived category of P1. This has multiple T structures. And some have Noetherian hearts. And some don't. So the same stable infinity category can admit many bounded T structures, some of whose hearts can be Noetherian, which will guarantee the vanishing of the negative K groups. Some won't be, so it wouldn't be obvious that the negative K groups vanish, although a posteriori they would, because there's another T structure on it that is Noetherian. Okay, so conjecture B is a direct analog of Schlichting's conjecture. So if A is small stable infinity category with a bounded T structure, then the same map is in equivalence, but without passing to the connective bits. That's conjecture B. And then conjecture C, this is the last conjecture that I'm going to write, at least for now. If A is stable, it doesn't really matter if it's small. Stable infinity category with bounded T structure. Oh, I misstated. That was conjecture C. What I meant to say here was that that was supposed to be conjecture B. That if A is a small stable infinity category with a bounded T structure, then all its negative K groups vanish.
So for n bigger than 0, is it minus?
Yes, thank you, for n bigger than 0. And then conjecture C was what I wrote there, with bounded T structure. Then the K-theory of A heart mapping to the K-theory of A without the truncation is an equivalence. Now you might be wondering, are any of these conjectures related to one another? And the answer is conjecture B is true if and only if conjecture A and conjecture C hold. So B is the real conjecture that we care about. Let me state one more conjecture. Let me call it D. Is if the, quote, Serotonin question, which I'm not going to, wait, sorry. This isn't even a conjecture. I just didn't want to conjecture what I'm calling the Serotonin question. If the Serotonin question holds and C holds, then B is true. What is the Serotonin question? Namely, if A is any abelian category, then you can embed it inside another abelian category B as a Ser subcategory. That's what the Ser part in the Serotonin question means. What does the cone mean? Such that K of B is identically 0. Normally this is accomplished by taking B to be a category with infinite coproducts. Then you can apply the Eilenberg-Swindle to deduce that the K-theory of any category with infinite coproducts is identically 0. However, you can't always embed A as a Ser subcategory inside an abelian category with infinite coproducts. There are counterexamples to that. You can look at remark 339 of the paper that I'm talking about, which is on the archive and published in Inventiones. So that will show you the counterexample to what is a seemingly innocuous statement. And we thank Jacob Lurie for that counterexample. So let me tell you what is true. So these are still conjectures. Now let me tell you what is true, and then I'll also tell you what T-structure is. At least indicate what a T-structure is, where it came from, and I think I'll be out of time, if I'm not already. So, what is true? So, the theorems that are true, that we prove in this paper, theorem 1, if A is a stable infinity category with bounded T-structure, then K minus 1 of A is 0. That's an adaptation of Schlichting's argument. It's a little bit harder in this case, but it's not really that much harder. What is significantly harder is this: if A is stable infinity category with bounded T-structure such that the heart is the Noetherian, then K minus N of A is 0 for all n greater than 0. And finally, theorem 3, under the same conditions. In other words, we need the Noetherian heart here. The theorem of the heart holds in full generality that K of A heart and K of A is an equivalence without just looking at the positive homotopy parts. Okay, not going to get into how these proofs go. Instead, I'm just going to tell you really quickly what is a T-structure, just so that you have some idea what's actually being talked about. So they were developed by Bailenson, Bernstein, and Deline to study perverse sheaves. So they first came up in the context of derived categories of coherent sheaves on various stratified spaces, and the perversity of the sheaves involved the exact stratification of the spaces. What is it? Well, if C is a stable infinity category, or a triangulated category, because really all the T structure only depends on the homotopy category of C, so it's actually an invariant of the triangulated structure. So a T structure is a pair of full subcategories. So I have the part which is supposed to consist of my connective objects. So in terms of derived categories, you should think of this as those objects in the derived category of an abelian category whose homology is 0 for I less than 0. If you look at this paper, they indexed everything cohomologically, but in homotopy theory, we index everything homologically, so I'm using the homological indexing. So I'm talking about chain complexes instead of co-chain complexes. Another category of my so-called co-connective things, so these will be those A's in this example, such that the homology of A is 0 for I greater than 0.
David, what's the word before the phrase of full subcategories? Third line up from the bottom. A T structure is a pair. Right?
Pair of full subcategories.
Everybody else.
It's those two pairs. It's the connective part and the co-connective part. And then I just have to tell you a couple, there's 3 easy axioms that they satisfy. Which mimic how homotopy groups of spheres work, or mimic how derived categories work. So you can check that these conditions are satisfied in cases of interest. So first of all, the first axiom is that the connective part, if I shift it up by 1, so what does this mean? These are all the objects of the form. These are all the objects B in C such that B is equivalent to the suspension of A for some A in C greater than or equal to 0. So that's what that notation means. I'm just shifting up the connective part. The axiom is that this is contained in the greater than or equal to 0 part. So if I shift up something that has no homology in negative degrees, it should stay that way. Oh, and the opposite, if I have something concentrated purely in negative degrees, that should be contained in something that's concentrated in purely negative degrees but shifted up 1. So that might have something, 1 positive degree. Axiom 2 is if A is in the greater than or equal to 0 part, and B is in the less than or equal to 0 part, then the space of maps from A to the shift down of B, this is contractible. There's only the 0 map from something entirely concentrated in non-negative degrees to something, well, B was concentrated in non-positive degrees, but then I shifted it down to it was concentrated entirely in negative degrees. So I only have the zero map there. And the third condition is, given any A and C, there's an exact triangle from that looks like this, where this part sits in the greater than or equal to 0 part, to A, to this, which sits in the less than or equal to 0 part, shifted down. And it turns out, and I'm not going to show this, that these truncation and co-truncation functors, or operations, are actually induced functors on the category, and hence a semi-orthogonal decomposition like that, which is why T-structures are also related to localization sequences. So I didn't, I guess I just should have said that finally, one more thing, because it's easy to produce T-structures. There's a purely categorical method for producing T-structures, but they're rarely bounded. So let me just give you two more notions that you need. So a T-structure is bounded if, well, I can look at the union over all n of the less than or equal to 0 part shifted down by negative n. Am I saying this right? Yeah. No, I wanted this. I'm looking at the stuff that's in positive degrees and shifted down by negative n, and in negative degrees shifted up by n. So this is all the stuff that's sitting in degrees between minus n and n. I take the union over all n. This is called C sub b. If this is all of C. And then finally, I should have defined the part for you. That's just the intersection of the less than or equal to 0 part and the greater than or equal to 0 part. So it's the stuff concentrated exactly in degree 0. The theorem of Balin, one of the theorems of Bailenson, Bernstein, and Deligne is that this is actually an abelian category. So that's how T-structures interpolate between stable infinity categories and abelian categories. And I told you the K-theory side of that already. If I had more time, I would have gone on to tell you some more K-theory computations that come out of this, but I will stop here.
Questions?
Yeah.
What K-theory computation? I mean, you can just mention them, I'm sure.
Well, I don't think they'll be news to you. I was going to talk about equivalent localization sequence and Devisage for a Dedekind domain, then the Blumberg-Mendel localization sequence, then the disproof of Robinson's conjecture. I mean, I'll spare the audience.
So when you mentioned the T-structures and connect the perverse sheaves, I forgot what a perverse sheaf is.
Right. Well, so did I. It's a type of coherent sheaf on a stratified space.
That's what I was, so it has to do with studying the geometry topology of stratified space.
Yes.
But they're not coherent sheets.
Constructive.
Right, constructible sheaves. On each stratum, I guess they're
No,
coherent. As you pass,
stratum, they're locally constant.
right, exactly. But then overall, as you pass from stratum to stratum, they jump. Yeah,
You said that negative K-theory of schemes encodes some sort of singularity data.
yeah.
What other information about the scheme can we recover from different K-groups?
Well,
Let me explain. What was the question?
Like, what sort of information does the K-groups and schemes?
The negative or the text?
I'll look at
that's a difficult question to answer. I think the way that you should think of K-groups is that either they vanish or they don't, or they're torsion or they don't, or they're not. And we're really at a really only very heuristic understanding of what the K-groups actually mean, but you should think of vanishing of negative K-groups as saying that the scheme looks like a regular scheme. And the positive K-groups are almost never going to vanish, but we also can't compute them. There's deep conjectures about whether or not they're even finitely generated that are completely unknown, even in the case of a regular ring, a regular commutative ring. Bass's conjecture is wide open, and that needs to be shown before we can talk more rigorously about the relationship between K-theory and L functions and zeta functions. Because if things aren't finitely generated, then these special values of L functions and zeta functions that are supposed to pop up out of the K-groups might not really be well defined. So there's no, maybe a better answer to your question is you can look at the regulator map from K-theory to motivic cohomology to try to understand better arithmetic information that's more readily read off from motivic cohomology. But that would be separate. Those are easier and more accessible somehow than the K-groups.
So the obstructions in your title, were they the negative K classes, or did you
Right,
have something more
I didn't quite get
sophisticated
to
in
that,
mind?
but yeah. So the negative K-groups obstruct the existence of bounded T-structures. I wanted to mention maybe why one would care about that in practice. But, I mean, in applications to, say, mirror symmetry, where you're considering Bridgeland stability conditions, for example, all of that is predicated on the existence of a bounded T-structure. So if there's a single non-vanishing negative K-group, there cannot be a bounded T-structure.
More questions? Let's take the
Yeah.